The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Alright, so I'm going to work through problem number 5, and this problem actually is a continuation from problems number 3 and 4. And basically this problem is asking us, what is the number of revolutions after 4 seconds when starting from rest? So in order for you to do this problem, is probably a good idea for you to have done problems 3 and 4. And if you can remember, we were talking about a wheel that had a radius r, which was 0.1 meters, and we applied a force so as to rotate this wheel. Alright? And in problem number 3, we were asked to find the acceleration, the angular acceleration of the wheel after we applied the force. And then in problem number 4, we were asked to find the velocity after 4 seconds when this wheel was starting from rest. So in problem number 5, we're now asked to determine the number of revolutions that this wheel is going to rotate 4 seconds after we apply the force. Alright? So we can it's probably good. I encourage you to use your formula or follow along with your formula review sheet. And again, translational motion and rotational motion are analogous to each other. And so some of the formulas that you have for translational motion will apply with rotational motions, except for that you, instead of using translational variables, you'll have to use the parameters for rotational motion. So for example, we know that that this problem is talking about we can imply this problem is implying that that we found the acceleration in problem 3, and we know that that acceleration is going to be constant. Right, because we're applying a force that's constant that was given 50 newtons, and if the force doesn't change, then we know that the acceleration isn't changing, and so the acceleration is constant. Okay, and since we're working with constant acceleration, we can go to our formula sheet and look into the section where it says for constant acceleration, and we've got several formulas that we can choose from. But basically, if we're trying to find rotation, we could use several. We can use at least the bottom 2. So let's look at this particular equation, where we have x is equal to x sub 0 plus v sub 0 t plus 1/2 a t squared. So this would be the equation for in translational motion. Alright? Let's rearrange this equation, because actually what we're really trying to find is the number of revolutions. Okay? But the number of revolutions really is just the distance. So that's the reason why we chose this equation here, because if we rearrange this equation, we get okay, we know that this is basically, we can define as delta x, okay? And this is basically our distance. Now, in rotational motion, instead of we're talking about distance, we're talking about basically the angle that we have basically traversed. And this angle is going to be in radians. Alright? And instead of velocity, we talk about our angular velocity. And instead of acceleration, we talk about angular acceleration. So our new equation would look like this. Okay. This is the equation for rotational motion that we want to use. And the reason why we want to use that is because we have all this information. We know that the initial angular acceleration is 0, so this whole term goes to 0. We know angular acceleration, or sorry, did I say acceleration here? I meant velocity. The angular velocity, the initial velocity is 0, so this whole term goes to 0. We know the angular acceleration from problem number 3, so we can simply find the distance that it traveled by substituting in this information, and angular acceleration was 0.17 radians per second squared, and the time is 4 seconds, and we're going to square that. And when we work this out, you'll see that the seconds will cancel out, and you're just left with radians. And that works out to be 1.36 radians. Now, that's not the answer to the problem, because the problem is asking us, what is the number of revolutions? All right? And we have our units in radians. But we do have a relationship between radians and revolutions. We know that if we're talking about just going in a circle, all right, we go in a circle here, we basically went around the circle once, or one revolution, and we know that one revolution is the equivalent to 2 pi radians. Right? Remember that this is 0, but when you go around, it's also 2 pi. Okay, 2 pi radians. So, given this relationship between revolutions and radians, we can convert that the number of revolutions is equal to whatever we're given in radians multiplied by a conversion factor, which is 2 pi radians and 1 revolution on top, so that our radians cancel out. So revolutions in this case would be 0.22 revolutions. So the trick to this problem is really understanding that we're talking about rotational motion versus translational motion, but understanding that they're both analogous to each other. And once you did that, you could have taken the translational motion equation, given constant acceleration, and just substitute in the rotational variables, parameters that's used. We had enough information to determine determine theta in this particular equation, and we got 1.36 radians. And then understanding the relationship between radians and revolutions, because that's what the problem was asking, we were able to use that conversion factor to convert radians to revolutions, and we got the answer. Okay.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.